let us ask this question, and this is maybe a lifetime question. You may not get the answer in your lifetime, or maybe you can. The world, whether the world is working in a fashion of qualitative nature or quantitative nature. Okay. But that doesn't resolve the, or even if we get the answer, that may not always help us in a sense that science, the modern science is developing. Okay. So let us go one step ahead and ask the question whether can we manipulate the world in such a way that we can evaluate it in a quantitative nature. Whether it is qualitative or quantitative, it doesn't matter. Can we evaluate and make it useful for us in a quantitative nature? So for that, the subject that is developed is mathematics. The understanding of the pattern of nature and use the logic to evolve with some assumptions, postulates and axioms. So you have to be careful that what are the assumptions. The nature doesn't give us assumptions. It is our human brain. For the ease of our calculation, we make the assumption, we make the postulate, and we make the axioms. And then we keep rolling on according to our so-called logic, uh, but it may sometime end up which is not matching with the nature. Then we need to say that whether our assumption was wrong, or postulate was wrong, or how we are arguing our logic was wrong. Okay. So that is the fact. And that happens not only once, many times in physics, in mathematics, and consequently any other technology and all those stuff, you will be seeing this kind of thing, that we assume this thing and we have done this thing, but now either the nature is destroying it or it is not matching with the thing. So it has many. Now what is the addition to this aspect is the assumption of randomness, which is not present in the structure of mathematics. Mathematics is very much clean and clear. Okay. And it is the beauty of mathematics that it states its assumption, postulates and axioms at the very beginning, and then it rolls according to the so-called logic. Other subject often forgets to do that. But statistics, apart from the assumption of mathematics, it adds another assumption, which is the assumption of uncertainty or the randomness, and as well as they consider a repetitive behavior of certain phenomena from nature, and they have the nature of law of large numbers. When the large population gathers or some event is repeatedly occurring with randomness still allowed, or the uncertainty still allowed, but repeat, what will be the ultimate nature if something is repeatedly happening? These are the thing that is not properly dealt in mathematics, but it is dealt in statistics, and that's why the statistics becomes very much close to the nature than mathematics. Mathematics is in the core, but if you want to match your ideas, your thoughts and developments from pen and paper or computer simulation nowadays, whatever may be, to nature, then without statistical aspect, that means with these two assumptions, you cannot match. Okay. Now let us go a little bit deeper. Does anything happen randomly in nature? Well, it has two answers. And no, under Newtonian physics. So if you go by Newtonian physics, every law has its own every action is its own reaction, opposite direction, whatever, and everything, whatever you can think of, can be assigned as a causal relation. So nothing will happen under the realm of Newtonian physics. But if you enter in the quantum physics, neither the theory nor the physical or the phenomena can happen without the assumption of randomness. Okay, So now what does appear to us something random? Because ultimately we are trying to deal with randomness in statistics. For the time being, what we can say that it is our incompetency to measure the or measuring capacity which makes us feeling something happening at random. So if you are flipping a coin and you don't know whether head or tail will come, but if you can measure the weight of the coin exactly, if you have the proper measurement at which location of the coin the force is exerted, if you know how much amount of force is exerted, if you know how much rotation it has taken in the air, and as well as how much friction due to the air resistance is there, if all those informations are correctly available, you can say that whether it will be coming head or tail with 100% guarantee. But you cannot do that, and that's why it appears to you as random. But it is not the same case when some experiment happens under the realm of quantum mechanics. Starting from the double slit experiments, everything, whatever you say, that the uncertainty principles governs everything. Now, let us see that how does statistics help us? Okay. So statistics tries to find the pattern even in random. So what people say that it is random and hold their hands up, we cannot do anything. Statistics can do something. It can still find some pattern in the randomness, and it can make use of that, and that makes the subject even more beautiful. The statistics admits the presence of error and gives the mathematical justification to control that error. Error will be there. Nothing will be clean and clear. But we can still deal with the error. We can still minimize the error, or we can still have a precision level incorporating the error. So that is the beauty of the subject statistics. And statistical analysis helps to estimate the value in forward and backward direction over time. So most of the statistical problem can be thought of in these categories, that model building, under which model it is working, so that you work with pen and paper or computer simulation, and then you can go for matching with the nature. So this is one aspect. Second thing is that you predict. Predict means because based on the model, some part you have fitted a model or constructed a model, then some part of the data known, some part of the data not known. So you want to predict that part of the data. If it is a time dependent scenario or chronological thing, uh, if it is a chronological thing, then there is a case that means either you can look into forward direction. Usually we do stock market data, weather prediction, rainfall prediction, all those stuff. Global temperature increasing or decreasing. Now they are shouting. We are saying, being a statistician, so for long days that the certain change has already happened. But businessmen, they know only money. As long as the water or heat doesn't enter in their house, they don't realize. So the thing, either you go by the forward direction or in backward direction. So if you are a physicist, you are most likely to be interested to know about how the Big Bang has happened, and how long back some stars has collided, and how from which source the gravitational field is emerging. So all those questions are interesting for the physics, and as it is interesting for the physics, it is interesting for all the sciences which is dependent on physics, because nothing is free from physics. Um, Even if your construction, even if your magnetism, so your computer device, whatever you can think of. If the change is happening in the physical law, it will affect everything. So you have to be careful. You just cannot ignore everything and then the development. So the so-called the too much specialization of our modern studies is sometimes make us paralyzed. So the the way the culture was for the development of science, that any people you see from little around maybe say 1500, 1600, 1700, they were aware of more than one subject in a very good depth. But now if somebody knows something, that guy knows only that thing and nothing else. So that makes a huge difference, and that may end up collapsing in the modern way of study. Let us see how happens. Now I'm not going into the much details of the. I will share you the slide. You can search and look for it. This is a development from the of the subject statistics from, maybe say approximately we can say that 1650 around. So from the definition of Pascal and Fermat, the mathematical theory of probability, and then gradually it evolves. Few of the remarkable milestones I have pointed out. I am not going for all of them, but here one of the important name you can see that the Bayes theorem, the idea of the conditional probability, that is introduced by in the name of Bayes theorem, partitioning and conditioning. Uh, I think all of you have done some work in probability in your 10 plus 2 level. If you have done, it is good. If you have not done, it is very good. Nothing to worry about. So, because 10 plus 2 level is not the proper platform to teach statistics. So if you have not done statistics or probability in 10 plus 2 level, then it is very good. Okay, so I am skipping this part, mentioning especially for the Bayes work, and then it continues. The Gauss, the very famous Gauss, he have done many remarkable work, and one of them is the predicts the orbit of the cirrus using the lines of best fit, the best fitting model first introduced by him. Then the ideas are evolving, and here you can see another common thing maybe you have come across earlier, the Venn diagram. Yes, any query? Okay. So frequency interpretation of probability. That is a very important thing, and it came by Venn. And you already know about the Venn diagram when you have studied the set theory. And interestingly saying that whatever the definition you will learn of probability in this class or in this course, when you have to use the probability or when you have to estimate probability, either through computer simulation or from the real data, you need to go by the frequency interpretation of probability. And that is the useful thing. Useful thing in practice, that definition will be used. Solving problem by pen and paper is separate issue, but when you need to estimate probability, then that is the definition you have to use. There is no other school. Rest of all of them are mathematical. This is only the practical. Now, in modern world, there are huge difference. Huge difference. I'm starting from here, 1933. Kolmogorov, he gives the first definition of axiomatic probability. And after that, it evolves by Fisher. He gives the design of experiment. Then Neyman and Pearson, they give the methods of testing and confidence interval. Then Cox helps us to develop. Students are requested to uh, mute their mic if you are not on. Then Cox gives the modeling structure for the logical data and the other variables. Then Shannon's gives the measure of entropy. Then Metropolis gives the simulation from the conditional distribution and what it is now the Bayesian statistics, how it has flourished. It is because of this different algorithms which are implementable with the help of computer nowadays. And then comes the famous guy Efron. He is still alive in Stanford. He is the emeritus professor. He gives the bootstrap, okay, resampling method. But not only the Western people, we being an Indian have a very long and strong heritage. And more interestingly, majority of them comes from Bengal. So here are few people I have mentioned. The list is very, very long. So Prashanta Chandra Mahalnavis, he is famous for introducing d-squared distance, standardized distance for the high dimensional data. And not only that, he is the founder of Indian Statistical Institute, and as well as he was the pioneer of the Planning Commission of India, Free India. Okay, then it comes, and he worked in Presidency College, Calcutta, as well as Calcutta University, and he is the founder of iCycle. And then comes A.K. Bhattacharya, Anil Kumar Bhattacharya. He gives the Bhattacharya bound. And Fisher, whatever is the Rao and Kramer's lower bound. If you go into the deeper subject of statistics, you will see there is a very famous Rao and Kramer lower bound, but that is a special case of Bhattacharya lower bound. And he was a professor from Calcutta University and colleges from Narendrapur Ramakrishna Mission and Calcutta. Then C.R. Rao. He gives the Rao-Kramer lower bound. He is famous for that, and many other contributions here. C.R. Rao. He was the director of ISI Kolkata, as well as many contributions. And I think he is still alive, more than 100. Then comes D. Basu, and he is famous for Basu's theorem. There is a very fundamental theorem, how the independence happens when you extract out all information about some parameter from the data. That was that penetrates the subject such a deeper that it is still the most celebrated theorem in statistics. There are many sophisticated theorems has come up, but the Basu's theorem is so profound, and he was the first research scholar of Indian statistical. So Basu's theorem is so profound that it is still considered to be the most celebrated theorem in classical statistics. Then K.R. Parthasarathi, he is pioneer of quantum stochastic calculus in India. And then let us talk about the name of Bharadhan. He is the Abel Prize winner, and his contribution is large deviation and many other. Then there is Varadarajan and many other professors. They have already contributed, maybe not working, and there are many other professors from India who are still working, not only in India and abroad, and still enriching the subject. So this is in modern world, this is one of the area where Indians have still a strong hold. So we can still feel proud of it, and it is our responsibility to keep it high and contribute in a significant amount of work to this subject. Okay. Now, few examples just to show how it is useful, not only in our old school of statistics, and it is useful in the modern world statistics also. So let us go one by one. So first of all, the production process. So when we go for the production process, different combinations of the raw materials are needed, and the similar thing you can consider not only company production, it can happen of the agricultural production also, and that, or you can think about the how the teaching structure. So whether the online teaching is better or the offline teaching is better, whether the slide presentation is better or the board work is better. So all these kind of thing can be compared with a proper structured design of experiment. So the design of experiment is one of the important aspects from where the classical statistics evolved. And there was one famous experiment by Fisher that a tester, tea tester, will distinguish between 2 cups of tea and or more than 1 cups of tea, saying that, or into 2 categories, whether the sugar is added first or the milk is added first, whether there is any change in the taste. So that is known as the very famous experiment called lady testing tea, and there is a book with the same name, Lady Testing Tea, written by a recent author. You can read the entire history of statistics, that how it evolves in that book. You can search for it and you can read it. The Lady Testing Tea. Another important aspect that is often used for the engineering field as well as the manufacturing companies, which is known as the statistical quality control. So whatever we are using, that comes to the market after a quality checking, and in the production process the quality is checked due to the specification provided by the client or by the manufacturer. And if there is an indication of the change in the measurement of output, say for example, if you are using a pen drive, then the pen drive must fit to the port of your computer or wherever you are taking. And with a pen drive you can move across the world, and it is supposed to work in all of the computers. If there is a minor defect, that means length, breadth, width, somewhere some defect is there apart from the technical software hardware part. Even if with the length, breadth, depth there is some defect, it will not fit. Either it is in the defect in the pen drive, or there is a defect in the port where it is supposed to be inserted. So those kind of things can be controlled, and the production process can be investigated through a method which is known as the statistical quality control. So for that there are many charts are provided and many methods are there. So they are known as the mean chart, standard deviation chart, and defect chart, something like that. And they comes under the realm of sequential analysis. They are always not a fixed sample, fixed time experiment. They are keep on running, and sequentially it is done. Another aspect that is regression. So as I have told that if there are data and it has more than one components, and if we know some of the components and if we don't know some other, then it is our duty to make a model, predict it, and then go. So either we can go for linear regression, polynomial regression, response surface in higher dimension. For categorical data, it is logistic regression. This is another aspect which is different from the previous. They are known as the survival analysis, when it deals with the human longevity and process which is affecting the human lifespan or reliability. That means the similar way of analysis done for the machine. Okay. So how long a machine will be surviving, how long it will be working, and what will be the replacement and all those stuff. Maybe replacement is not possible for human, but for machine it is possible. So there are many aspects, and the challenge is that uh, here we need to wait for the failure. That means something breaks down and then the data will be collected, then the analysis will be done. So it is depending on the lifetime distribution or the failure distribution, something like that. And the Cox model, I have already talked about it. The Cox model is a very famous model for that. It is applicable for the insurance policies and the censoring scheme, which is, I don't know whether this year India will conduct a census or not, but usually, I mean, this 2021 11 in this way, that after a gap of 10 years, the India conduct a census. So, okay, and now you come for the recent time, well, I mean, huge discussed topic about the biomedical statistics or the clinical trials. So here the main objective is this, that when we need to compare more than one drugs which are supposed to be launched in the market, uh, then we cannot give 50% patient to the one drug and another 50% patient to the other drug. So it might happen that uh, it usually happens that one drug is superior to the other. So ethically, I cannot send 50% student, 50% candidate to the inferior drug and 50% to the superior drug. So we need to evolve the experiment in such a way that the less number of patient goes to the inferior drug, but we can compare the treatments according to a certain level of pre-specified accuracy. So that is the main objective of adaptive design in biomedical statistics. Okay, and then the adverse drug reaction. After taking the drug, what is the cause of the reaction, and genetics. All those stuff comes in the biomedical statistics. Then comes the time series analysis. It is very common examples, that weather forecast, stock market analysis, business policy making, astronomical statistics, and signal processing. All those stuff. Either you can go in forward direction or backward direction. They studied under the time series analysis. And few other topics are like this, that complex network studies, social media, growth of the social media, the application of the advertisement, and the network. So these are very common things that you can come across. And then now it is very common, almost everybody, irrespective of any, you can see that there are so many departments in IIT Kharagpur, but uh, almost all of you are interested in machine learning and all those stuff. So it has ended up with 7 sections now, and still people are waiting for as an additional to take this subject. So anyway, it has application, statistics has application to the statistical learning theory, which you implement as a machine learning. So clustering, classification, image processing, safe analysis, behavior analysis. So all those stuff are studied under statistical learning theory. And recent developments are algebraic statistics, uh, statistics on manifolds, random field theory, and functional data analysis. So these are the cutting edge work that is still developing in the as a theory. So this is the introduction, that where and how the statistics can be applied and how it is useful. So I hope, I mean, that the students and the attitude in this atmosphere of IIT education, people always ask that what is the application. So I think I have talked about many applications. Now we will be developing the theory for that. So please keep all these applications in mind, such that you don't I mean, get depressed with the theory, because without proper theory, application is not going to work. Or if it work for some example, it may not work for the other, and then you may end up with a wrong conclusion. Okay. So a proper theory is needed, because when the range of application is so huge, the theory should be even more stronger, which can take care of many possible cases. And just give me to give you this idea that these are in AI/ML. People are nowadays talking, so that I thought that I add this part. That for AI/ML portion as an application of statistics. So what are the things that people do, whether they admit or not? They automate data entry, detecting spam, product recommendation, medical diagnosis, covariate, corrective and preventive measures, speech detection, image or video recognition, that is comes under computer vision, natural language processing, video, online games, etc. All those kind of stuff are dealt in AI/ML kind of problem. Now, in the back end, they all can be finally classified into either clustering problem, classification problem, regression or forecasting problem. Okay. And to do that, what are the statistical thing that you need to know? That for that you need to know estimation and testing. For that there is a course, statistical inference. After doing probability statistics, you must go for that. Interval estimation and model selection. It can be done in a parametric, non-parametric and Bayesian structure. And to do that, what are the mathematics needed? The needed mathematics is linear algebra, functional analysis, differential geometry, topology, graph theory and optimization. These are the structure on which the statistics works. And what are the computer science stuff needed? The data storage, data retrieval, memory estimation, signal transmission, data visualization, automated service, automated learning. So these are the interrelated things which are working in the back end of statistics, machine learning or AI/ML kind of thing. So statistics is a pillar of that, which is working on mathematics, and the computer science thing is combining these two, or gluing these two things together. So I think enough of the introduction. Any query before we enter into the topic? Any query? Hello? Okay. So I am asking you 3 questions. Okay. Very simple 3 questions. You may know the answer. That doesn't matter. But you have to tell me what are the difference between these 3 questions. So first question is this. Consider a deck of cards. Okay. From 52 cards, a card is randomly chosen. What is the probability that it will be black? First question. Second question is, a random number is chosen from the set of natural number. What is the probability that it will be an even number. And third query is this: a random number is chosen from 0 to 1 interval. What is the probability that it will be less than 0.5? Okay, so tell me the answer first. Is the question clear?
Yes, sir.
Yes. So please tell me the answer one by one.
The first is half.
First is half. Okay. Why?
Sir,
Sir,
either
because
red
there are
or
equal
black.
number of red and black cards.
Okay, it has 23 cards red and 26, right? And 26 cards red and 26 cards black. Okay. Half. Second one,
Half,
half.
sir.
Half.
0.5. Half. Half. Half.
Either the
Why?
number would be even or it would be odd. Means both are equal.
Both are equal. Okay.
But sir, like they are
Okay.
infinite in numbers, then how can we say?
Yes. Okay. Question raised.
So it will also depend on whether the set we are considering that if it is ending at a even or odd number.
The set is infinite set, sir. Since it is all natural numbers, we don't know what's the end. I mean, there is no question of asking what's the end number.
No, sir, we
Yes.
have to go that side.
Right.
No, sir.
Right.
A number can be even or odd. A number can be even or odd, no, sir.
Okay. Yes, it can be
So
either
in
even
this
or
case,
odd.
the sample space is infinite. So
Mhm.
I think it will be
Sir,
difficult for us to
sir,
tell
Yes,
as
you
about
have
the
the
one
number
question.
of
probability.
natural number tends to infinity, sir probability is also tending to 0.5.
Okay. Okay.
Yeah, but there are same number of natural numbers as there are even numbers. So
Mm-hmm. Yes.
that number of even numbers is equal to the number of natural numbers. So
Number is equal to the natural
So it
numbers.
kind of like, sir, there is no upper bound in the set. So we can't
We.
comment about, like, if we consider a small set, if the last number
Mm-hmm.
is a odd number, then the
Mm-hmm.
probability will be different than if the last number is a even number. But if it is an infinite set, then it will be difficult to comment on what will happen at the end.
Okay. Okay. So
And all
confusion is
with
there.
usual probability
Yes.
definition which we learned in plus 2.
Okay. Okay.
Favorable cases by total
Any other?
cases.
Okay. Yeah. Yeah. Thank you. Thank you. And any other comment?
Yes, sir.
Sure, we could directly like consider if there are n numbers and we could find the probability, and as n is tending to infinity, we'll find that the probability is also tending to 0.5.
Okay.
It will be slightly less than point.
Yes. Limit we can.
Yeah.
Okay. Okay. Thank you. And the last one.
So it will also be 0.5.
0.5.
it will also be
I think it will be
Now.
a slight less than 0.5.
The
Yes.
slide
So it
It will
so
be
we
taking.
can so it will be 0.5 only because we can classify it less than 0.5 and more than 0.5. So any number we choose will either lie in the first quarter or the second quarters, and from on the basis of that we can say that it will probably be 0.5.
Okay. So the thing is that answer to all of them technically is 1 by 2. But the definition used to evaluate this one is different from this one, is different from this one. And we have to introduce all of them. Okay. So that is the goal of, I mean, the first introductory class of probability. Because I hope all of you are quite familiar with the classical definition of probability. So here what we use is the classical definition. Here what we use the frequency definition. And here what we use the axiomatic definition. And let me tell you that axiomatic definition is designed in such a way by Kolmogorov, just I have told you, in 1933, around like that, a Russian mathematician. And interestingly, that the way we write mathematics nowadays, and sometimes also physics, that is the contribution or the influence by Russian and French. So once in a time they have developed the modern way of writing mathematics is influenced by them. So the way we have written, or many other parts of the country have, the world has written mathematics, that is different, or the writing pattern or the mode of communication is now completely driven by this French literature of mathematics and the Russian literature of mathematics. And one of the pioneer is Kolmogorov, and he has given this axiomatic definition. So this axiomatic definition engulfs the frequency definition as well as the classical definition. So we will gradually introduce classical definition, frequency definition, and axiomatic definition. But when you will see the axiomatic definition, these two will be a special case of axiomatic. So this is the most general one. Okay, so to go there, so let me start one by one with the classical definition examples, and let me ask you a few more small questions. So question one, it is a very simple question, just to refresh your memory. And so n balls are there and r boxes are there. So how many ways you can put the n balls in r boxes? So n balls, r boxes. And how many ways we can put? How many ways you can put n balls in r boxes?
So which is greater?
Any condition?
Say again, please.
Can we leave anyone empty?
Which is greater, sir? Is it n or r?
It is n plus r minus 1c.
Oh, you can put any ball anywhere.
Sir,
Sir, R
n
power.
It doesn't matter. R power.
R power है.
R. Very easy. First, we are doing counting. After that, something we will put in numerator, something we will put in denominator, and we will get the probability according to the classical definition. So first, let us do the counting, and then we will go. Okay, now n balls are there, numbers, numbered. That means they are distinct. And let me tell you here that if nothing written, especially for the question paper, if nothing written, you have to assume that the balls are distinct. There are many arguments comes after the exam and all those that. So I have assumed they are identical. No. If nothing written and just say for example, n balls are there, you have to assume they are distinct. And how many ways you can throw or choose r balls out of them? Choose r balls out of them. How many ways?
And we are
N choose r. This is a very pretty simple thing, but I am saying because they have some interesting name. And so n identical balls are there and r numbered box are there. N identical balls and r numbered boxes. You have to distribute in such a way, or maybe just you have to distribute n identical ball in r boxes. And let us consider, say, r is less than
n plus r minus 1 cr minus 1.
n plus r minus 1 cr. Okay, how? Can you please tell me?
x1 plus x2 plus x3 and so on, xn equal to n. xr equal to n.
Acha, n plus r minus 1 cr. Okay, okay.
Yeah, r minus 1.
Yes. So what is
r minus 1. R minus 1.
R plus 1 or r minus 1? What are, tell me correctly.
R minus 1 denominator.
R minus 1. Okay. So why? Why?
Sir, we can
use the stars and bars
consider
argument.
So it can be formulated in many ways. One of them is that you have n such identical balls. So among them, how many gaps are there? N minus 1 gaps are there. And in those gaps, if you want to make a partition, or you want to place a bar, or the two bars can come also together. So n minus 1, n balls, n minus 1 gaps are there, but you can, among these gaps, or you can make it a partition of through r minus 1 such bars. So you can have in this way that n balls and r minus 1 plus symbol so they are identical, and they are identical. So how many possible arrangements are possible there? So the number of ways you can arrange them is n plus r minus 1, choose r minus 1. And if there is how will you count? You can say that this is in the first box, this is in the second box, this is in the third box, this is in the fourth box, fifth box is empty, sixth box there is 1, something like that. The same problem can be reformulated just to ask in this way: sum over xi, I running from 1 to r, 1 to r equals to n, and r is less than n, and xi belongs to natural number or union 0. So this is another way of asking the same problem. How many possible solutions are there for this equation? The answer will be same. Now, why I am saying these few examples? This statistic has a name. This is due to Maxwell and Boltzmann statistic. This is known as Fermi-Dirac statistic. So physicists have introduced all those stuff, and this is known as Bose-Einstein statistics. Bose, our Satyendranath Bose from India. Now can you please tell me, if I don't include the 0 here, how many possible solutions will be there?
N minus 1 CR.
N minus 1 CR minus 1.
N minus 1. So only natural number solution is N minus 1 CR minus 1. So this is the counting part. Now if I ask this question, say for example, you have set such an equation in a computer, and computer will give you one solution. What is the probability that it will be only the solution with natural numbers? No 0 will be there, or xi will not take value 0. So what will be the answer?
N minus 1 CR minus 1.
No.
Divided by n plus r minus 1.
Divided by, yes. So we are using the classical definition. That means the number of all possible cases divided by the number of favorable cases. So the thing we define, we will make it formal tomorrow, that if this is the equation set under the restriction that it will be either the natural number or 0, then all possible, the number of all possible outcomes is this, and a subset of that will not contain 0 as a component of the solution, and that number of solution is n minus 1 choose r minus 1. So this is all possible cases, and this is the number of all, and this is the number of favorable cases. So the number of favorable cases divided by the number of all possible cases, that will be the probability according to the classical definition. So we will introduce formally classical definition tomorrow. Before that, we need to introduce the random experiment. What do we mean by random experiment? And from there, we will talk about the definition of classical definition of probability, frequency definition of probability, and the axiomatic definition. So I think that's all for now. Any query before you leave? I think pretty simple thing we have talked today.
Sir?
Yes, please.
Sir, will you share this handwritten notes also?
Yes,
no,
yes, everything will be uploaded in MST.
Okay, thank you, sir.
Sir, in the second question, what is the name of the statistics? Tell me, the second word is guarded.
This one?
Yes, sir.
Fermi Dirac.
Thank you, sir.
Fermi Dirac.
Sir.
Yes, yes. Yes.
Sir, for the first question, will the answer change if the boxes are identical or they are distinct?
The boxes are identical or distinct.
Sir, if boxes are identical, answer will be 1. There is one way, just put all of them in any box, I think.
No.
No.
It
Answer will be different.
Boxes are
Sir, if boxes are identical, then it is just a question of partitioning natural numbers into n partitions.
R partition.
Yes, R partitions.
Yes, sir.
Yes, yes.
And sir, in third case, the means boxes are non-identical, right?
Here?
Yes, sir.
This one you are saying?
Yes, sir. Because you have written R numbered boxes.
R number, they are not identical. So that means this is for the first cell, that means first box, second box, so they are numbered. They are not identical, they are numbered.
Okay, sir.
Okay. When numbered, then no chance of identity. You have got your roll number, not identical with any. Right? Even if your twine is here, still you are not identical. Got it?
Yes, sir.
Okay. Thank you. See you tomorrow, early morning, 8 o'clock.
Thank you, sir.
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 Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.